Looking back at the history of astronomy, we have to admit that human potential is limited in comparison to the universe. The farthest human-made object, the Voyager 1 probe, has only journeyed a distance of 0.00238 light years. Our spacecrafts have explored few planets, including Mercury, Venus, Mars, Jupiter, and Saturn. Humans have physically traveled to only one celestial body, which is our moon. Although we have yet to venture far beyond our solar system, our scientists and astronomers continue to uncover valuable information about distant planets and stars. For instance, they have discovered that the Betelgeuse star comprises 70% hydrogen, 28% helium, and 2.4% heavy elements, making it slightly more matter-rich than the Sun, but otherwise comparable. How did they know that? The secret is light. Just a little light is enough to tell us about stars, their composition, temperature, motions, and other crucial information. This technology is called spectroscopy. But before explaining how spectroscopy does the job, we need a little background about light. Scientists understand light as wave, like wave in the ocean. Ocean waves have high and low water levels that travel in a particular direction, and the distance between two highs or lows is known as the length of wave or wavelength. In light, instead of water level, we have electric and magnetic fields. Like ocean wave, these fields also have high and low regions, and the wavelength is the distance between two highs or lows. Wavelength of light can vary from very short to very long. Light with shorter wavelength carries more energy and penetrates deeper into the material. The interesting part is our weak human eyes can only see light with wavelength between 380 and 780 nanometers. We call this the visible spectrum. Light with wavelengths over 700 nanometers include infrared radiation, microwave, and radio wave, while light with wavelengths shorter than 400 nanometers consist of ultraviolet, X-ray, and gamma rays. Although they are usually not called light, and you can see all of them, they're all part of the same light spectrum. Both visible and invisible light can be emitted by objects around us or even by us. Glowing things like the sun, molten glass or lava give off visible light, while cooler objects like a rock or a tree release infrared light. To study the light an object emits, we need to use a nifty device called a spectrometer. The spectrometer contains prism and separate light with different wavelength. The device then measures the intensity of each wavelength, collects data, and sends it to the software to be analyzed. The ultimate result of that process is a spectrum. A light spectrum can be illustrated as an image, like this. However, it's best to plot on a graph to study it more precisely. In a spectrum graph, the horizontal axis presents the wavelength in nanometers, and the vertical axis presents the light intensity at each wavelength. You might recognize that the image version of a spectrum is actually what we see when we look at the graph version from above. Stars and planets usually emit a nearly continuous spectrum of light. This continuous spectrum contains a wavelength within a specific range and resembles an asymmetric bell. Just by looking at the shape of the bell, we can quickly determine the temperature of a celestial body. In general, hotter celestial objects are brighter, emitting more colors toward the blue end and therefore have a bigger curve. We can see the blue line presents Sirius A, the brightest star in the night sky, with a surface temperature of around 9,940 Kelvin. The spectrum peaks in the blue-white region, contributing to its bright bluish appearance. On the contrary, cooler stars are less bright, emitting more colors toward the red end, and generate smaller spectrums. Below the blue line is the yellow line representing our sun with a temperature of about 5,500 K and a peak in the yellow region. The red line can present stars with lower temperatures, for example, the Betelgeuse star in the constellation Orion. If you look at the spectrum of a star more closely, the bell curve is actually not that smooth. There are some dips in the curve. These dips are the result of the interaction between atoms on the surface and the light emitted from the core of a star. So, imagine the core of a star emitting a continuous spectrum consisting of all wavelength. When light from the core passes through the surface, element on the surface can absorb that light and become excited. Each element can absorb light with some specific wavelength. For example, hydrogen can absorb the wavelength of 656 nanometers, copper can absorb light at 470 nanometers, lithium at 670 nanometers, and barium at 554 nanometers. This absorption makes light with specific wavelength disappear, leaving dips in the spectrum graph and dark lines in the spectrum image. By looking at those patterns, we can tell what elements a star contains and the concentration of those elements. For example, the spectrum of our Sun exhibits many dips in the graph and dark line in the image. We see lines named C, F, and G indicating the presence of hydrogen, while the line D1 and D2 indicate sodium. Besides the temperature and composition, spectrometry can also tell us about the motion of a celestial body, thanks to the Doppler effect. If you're wondering what the Doppler effect is, imagine an ambulance siren. When the ambulance moves towards you, the sound waves are squeezed together, resulting in a shorter wavelength, with the ultimate result being that the siren sounds higher pitched and louder. However, as the siren moves away from you, the wavelength becomes longer, resulting in a quieter and lower pitched sound. This same concept can be applied to all waves, like the electromagnetic wave. If a star is moving away from us, all the light it sends to us will be stretched out and the wavelength will become longer. This makes the whole spectrum being nudged to a red end. We call this a redshift spectrum. The exact opposite happens when a star moves towards us. The wavelength becomes compressed and the spectrum will shift toward the blue end of the light spectrum, known as the blue shift spectrum. The faster the star moves, the more those lines are shifted. For example, while the spectra from Virgo is redshift, the spectra from Ursa Major is redshift even more, which means that although both are moving away from us, Ursa Major is moving much faster. Inferring motion from spectroscopy was the cornerstone of the discovery that the universe is expanding. Edwin Hubble, inventor of the Hubble telescope, found that distant galaxies show redshift, with the redshift being more pronounced in the further a galaxy is. This suggests these galaxies are moving away from us at speed proportional to their distances. Ultimately, this led us to discover Hubble's law, which says that the velocity at which a galaxy received is directly proportional to its distance from us. Simply put, the galaxy is constantly expanding. The spectral lines we see in a spectrum can also tell us how dense a star is. As can be seen, the blue zant has much narrower and sharper lines than the white dwarf, which has much broader and fuzzier lines. The exact cause is a bit complicated, but basically, the amount of pressure in the white dwarf is so significant that the energy levels in the atoms are disturbed, which then causes the line to spread out. Another way to study the density of a stellar object is to calculate its gravitational field. This calculation is based on an effect called gravitational redshift, which stems from Einstein's theory of general relativity. Another redshift effect. Gravitational redshift occurs when light from an object in a strong gravitational field is stretched or extended and goes into the radio wavelength. This happens because the gravitational pull of an object affects the energy of light as it moves away from the source. An easy way to picture this is to imagine light trying to climb out a very deep well. The higher the light climbs, the more energy it loses, and this causes the color to shift towards red. The more gravity there is, the more the light color will shift to red by the time it reaches us. By examining how much the light shifts towards the red end of the spectrum, we can determine how strong a gravitational field is that the light had to pass through. Let's use a white dwarf stars as an example. White dwarfs are a remnant of older stars which don't have any more nuclear fuel and have collapsed under their own gravity, becoming super dense and small. By measuring how much light is redshift, we can deduce both the size and mass of the white dwarf. For example, we have calculated the white dwarf Sirius B weighs about 98% of our Sun, and it has a density approximately 92,000 times of our Sun. Whether we are talking about temperature, motion, composition, gravity, or density, spectroscopy is a fantastic development in the world of astronomy. Spectrometers allow us to deduce a wide variety of facts about celestial bodies like stars and planets, which we would otherwise never be privy to. If you enjoy learning about the wonderful world of the cosmos and so much more, please subscribe to our channel. There are plenty more educational and exciting videos coming your way.